Hello and welcome to EP2P04. This is going to be the Topic 7 practice problem video on shear, and we're going to be using test number 7 from 2019, which is a pretty good representative thing to look at because the content is the same as it was in that year. Some of the earlier topics, this was topic 6 a long time ago. It was topic 7 as of 2018 and 2019. Okay, so a rectangular prism is made of a material with a Young's modulus that's 50 megapascals, not gigapascals like we've usually had, but just 50 megapascals, and has a Poisson's ratio of 0.3 and these dimensions. So it's shorter in x than it is in y and z. The prism is fixed on its y equals 0 surface and has a force of 50 newtons evenly distributed over its y equals ly face in the positive x direction. Now we're asked, by adding other forces to some of the other faces, maybe the x and z faces, of the prism, we can put it into pure shear static equilibrium. What other forces are necessary? So, given that we have a force on the y equals ly face in the x direction, that means we're going to be having a stress on that face, which is tau y in the x direction is equal to the force on y in the x direction divided by the area of that y face. So from the, maybe it's better to draw this out and sort of see the geometry there. There was the image to correct the more circle thing from the other video. Let's see. We've got x is 1 and y is 0. Let's just draw the XY plane here, and we'll kind of visualize what's going on there. Right. So let's see, this is going to be x, and that's y there. And we'll draw a rectangle. It's not as long in x. Whoops, rectangle hit O twice. Not as long in x as it is in y. So maybe something like that. It has a length of 1 meter in x and 2 meters in y. Okay, and now we are putting a force on the y equals ly face, so that's y equals 2 meters face, this top face, and it is a force in the x direction, 50 newtons. So this is what we've got applied here. Let's go maybe red there, and we'll draw it like that. It's in the x direction. This is the force we've applied, 50 newtons. Okay. And then this surface, the bottom surface here, is fixed. How could we draw that? Maybe we'll get some things here and kind of pretend it's anchored. Oh, that's not. I don't know how intuitive that is, but it's fixed on this surface, so it can't move on that bottom surface. We've shown it sort of like sewn into the bottom. So, oh, that's sort of kind of looks disturbing. Well, anyway, it's like stitched into the bottom. Maybe this is like some Frankenstein block because it is October, so 'tis the season. Right. So we've got something that has a fixed support here on the bottom surface and can't move on that surface and has a force of 50 newtons over to the right on the top. Now, to put this into pure shear static equilibrium, to make sure we don't have to apply a moment on the bottom surface, we're going to need to put a force on the right surface, which is in that direction, and a force on the left surface in that direction. Now, what force we're going to need to apply over here, maybe we'll call this F on X in the Y direction, and then we'll need also the same force over here, but in the opposite direction that's kind of pointed down. So we're not labeling, this is not the name of the vector, right? It's italic here. This is telling you the component of this vector that's in the up direction and the component of this vector that's in the down direction. Yeah. So the setup that we've got here shows us what we're looking for. We are going to need forces on x and y and on negative x in negative y, which have enough magnitude that they cancel out the couple produced by this force on the top and the 50 newtons we're going to have on the bottom. You could have had a moment applied on the bottom to cancel it, but then it wouldn't be in pure shear. So we can say that the force on the bottom is going to be 50 newtons, and this creates a couple, which is 50 times 2 meters. That's the y height there. And so that means in the x direction, we're going to need some force, which would produce the same couple of that 50 times 2, 100 Newton meters, by the yx forces of, let's say, the 50 Newton Fyx forces is Ly times Fyx, what's that, into the page, right? So that would be mz equals that, which is equal to negative 100 Newton meters. So we need Fxy to be 100 newtons so that the couple created by the force on the right face in the up direction, in the positive y direction, and the force on the left face in the negative y direction, so that those forces create a couple of mz is, that'll be this Lx times Fxy is positive 100 Newton meters, and the thing can be in equilibrium. Technically, I guess I should put a little dash there between newtons and meters to make it show that it's two different units there. And because Lx is 1 meter, that means Fxy has to be 100 newtons. Okay, another way that you could have solved this, alternative solution, need the same stress applied. Well, actually, we needed enough force on the x faces that the stress can be uniform. So that means the top face gives tau yx equal to 50 newtons over its area of the y face, right? And the area of the y face is Lx Lz out of the page, right? And Lz is 2 meters, so this is 50 newtons over 2 meters squared. So this is going to be 25 Pascal. All right, so that means we need to have then that on the right face, on the right and left face, tau x in the y is also equal to 25 Pascal. But that requires that the force on those faces which is going to be the shear stress times the area of those faces, is equal to the 25 pascals times, what's the area of the x face? That would be Ly times Lz, which is 2 meters times 2 meters, so that's 4 meters squared. And that again gives us 100 newtons. So conceptually, we can say that because these faces are twice as close together as these faces are, you need double the force on them to produce the same couple and put this in static equilibrium. And that means that you need exactly the same stress on this side as you have on the top. So that's part A. Let's see. Part B is going to be calculate the displacement of the center of the y equals Ly face when those other forces are added using Maple. So when those other forces are added, then we've got the thing in pure shear. So with those forces, the object is in pure shear. Let's see, uniform pure shear with tau yx equals to tau xy equals 25 Pascal everywhere. So everywhere it's true that tau yx equals tau xy, but now it's true that this is the same stress that we have everywhere. And since the bottom surface is fixed, that means that we can get the so, okay, first of all, this leads to, let's put it like this. This leads to a uniform shear strain of gamma yx, or gamma xy, is equal to the shear stress divided by the shear modulus, right, where G is equal to E over 2 times 1 plus nu. Right. So then once we've got the shear strain, so shear strain is this by shear stress over shear modulus, and gamma yx is equal to del U by del y plus del V by del x. But the V displacement is going to be 0 everywhere because we're fixing so the bottom is fixed to have no y displacement, so all of the displacement that's going to happen is just going to be in the x direction. Right. So we have no change in the vertical displacement per step in x because we fixed the bottom surface to the ground, so that means this is going to be expressing the shear strain by totally just moving the top face to the right. Because we've fixed, just to put that in words, because we fixed the bottom, this requires V equals 0 at all x's. At all x values there. So del V by del x must be equal to 0, meaning the shear strain is entirely due to del U by del Y. And if it's uniform, and well, I guess I should say since it's uniform, that means that gamma yx is equal to, in fact, the delta U, the total U, delta x, like U at Ly over Ly. Right, the total change in the x displacement when we get to the top surface, the displacement of the top surface, divided by the length, right? The change in displacement from the top to the bottom doesn't move, which is just going to be then U at the top, divided by the length in y. So U at the top center is going to equal Ly times gamma yx, so the length up to the top times the shear strain that we calculate, and the shear strain is equal to the shear stress divided by the shear modulus, and the shear modulus we can write in terms of E and the Poisson's ratio. Okay, so let's do that in Maple. We've got a setup where, actually I think that last one was one we did in the lecture notes, and it's going to be pretty much the same because this is exactly what happened in the lecture notes. But let's build it up again. So we've got Young's modulus, which is how much? 50 megapascals. 50 E6, and we've got Lx is 1, Ly is 2, Lz is 2, and then we've got a force, which is 50. Now this, what force is this? This is force y in the x, and that tells us what the shear stress is. Tau on y in the x is equal to Fyx over the area of the y face. And we can mess we can put in what the area of the y face is. First, by saying AY is equal to LX times LZ, which should be 2. And then the shear stress, as we calculated before, is 25. And then we can get the shear modulus. G is E over 2 times 1 plus nu. So it should be smaller than the Young's modulus. Oh, we didn't put in what nu is. Nu is 0.3. Okay. So let's see. We've got 50 megapascals, which is 5E7, and we've got about 2E7 for G. So this means, yes, we have a shear modulus that's on the same order of magnitude as the Young's modulus, but a little bit smaller because of this thing being greater than 1 here. Okay. So next, we can figure out what the shear strain is. Gamma yx by taking shear stress and dividing by G. And we've got a shear strain, which is 1 E minus 6. Then we'll convert that to a displacement, U at the top center, which will be Ly times gamma yx. Since we have no vertical displacement, all of the shear strain is going to be expressed as x displacement per step in y. So at the extreme far y surface, we're going to have the most x displacement, which is just Ly times gamma yx. And that's going to be 2.6 microns. Next thing is to go to part C. I've copied that code in for the end of part B. And in part C, what we can do is model the prism subject to all those forces and constraints in FlexPDE. So then find out what the displacement is and show a deformed shape and output contour plots of the axial stress in the y direction, xy shear stress, and yz shear stress on the y equals 0 face. So let's do that. We're going to start with the code that we made in the lecture notes and modify it. So we'll keep this magnification because that's kind of nice for showing a deformed shape and we don't have to mess with that. Then we'll set up the dimensions. It's 1 by 2 by 2. Young's modulus of 50E6. The applied stress is going to be the 50 Newton force divided by the area of the y face, which conveniently is already that. And we have a Poisson's ratio of 0.3, not 0.4. Okay, so then what else are we going to do? We're going to fix the y equals 0 surface. So this is the one that's drawing the square that's aligned with x and y again. The y equals 0 surface, that's fixed. Okay, so far so good. Then the x equals Lx surface. We will need, actually this is exactly the same stress that we were applying already, right? On the y equals Ly surface, we have a force in the x direction. On the x equals 0 surface, we need a force in the negative y direction. And so there we go. Okay, so then we'll just need the contours that they're looking for. They asked for contours on the, well, actually, I guess we'll also need the displacement. So first we should output, we got a lot of reports there. Let's get rid of most of these and just put in what we actually need. I guess we'll kind of put this out. Report what? Report U at half Lx, sure, and then all the way Ly, and then half Lz. Yeah, that would be the center of the top face. And that's the only report. We need a contour map that, so we'll get the deformed shape that's there using appropriate magnification. That's happening by default now with that code we put in up there. And then we can also output the axial stress in the y direction. That's Sy. And we need this where? On y equals 0. Y equals 0, painted. Okay. And we need all the contour plots on y equals 0. What are the other ones they wanted? The xy shear stress and the yz shear stress. All on the y equals 0 face. Okay, so this should do it. Let's see. Yep, so there's our deformation. Notice it's smaller in x than it is in y and z. All right. And we've got a contour map of the YZ shear stress, which is just 0, and the axial Y stress, which is also 0, and the XY shear stress, which is a fixed 25. Okay, and we've got indeed this, let's see, 2.6 microns. Is that what it was? Yeah, 2.6 microns. All right, so that's it. We've got it. So I've also put pictures of that in here, a little bit of a summary statement, and then included the code that I used to generate that. Okay, so next thing, we are going to go to question D. So this one says, now remove any forces that you put on the X or Z surfaces to achieve the pure shear, and use FlexPDE to model the prism, subject to only the fixed supported Y equals 0 and the original forces on Y equals Ly. So what this means is that we're going to take these side ones, the X surfaces, and get rid of the applied load that we put there. Okay. Now, the question asks, what's the displacement of the center of the Y equals Ly face? Now, show a deformed shape, and then output contour plots of those same stresses as before. So, what we've done now is we've just fixed this bottom surface, and we've let the rest of it be totally free to do whatever. So it deforms like this, and it's not so obvious from the picture because that's auto scaling, but the deformation's a fair bit more, right? We've got almost like what, 8 times as much force, rather displacement, as we had last time. So when we don't put those balancing forces on the side to force it into pure shear, then it bends a lot. You can imagine this thing is going to do this sort of deformation unless you stop it by putting those forces to say, no, keep your parallelogram shape. None of this funky bending stuff. That's not till next week, right? So, yeah, this has more displacement when we got rid of that, those shear forces on the side, and that's because it is now in bending. So displacement is higher, 1.8 E minus 5, so like 18 mu meters, so 18 micrometers. You can turn on the option in Word to accept the math shortcuts outside of math areas, so you don't have to go Alt equals and type your equation. Mu, you can just kind of get that outside of a math area if you put that option on. Anyway, so displacement is higher, 18 micrometers, and we've got a bending shape. It's not a pure shear shape anymore. In particular, you can look at these other plots. We've got some non-zero XY stress. I mean, it's remember we had XY stress before. It was just like 25, but now it's ranging around that. So it goes from 25 down to negative 30 and up to positive 80 at the sides. Look at this. We have a lower amount of XY stress here and here, but then we've got a higher amount on those sides. Wow. Now what about the YZ shear stress? Well, this is not 0. Now that we're not putting that counteracting, those counteracting forces to force the only stress to be this XY shear stress, then all kinds of crazy stuff happens, right? We've got some shear stress on Y surfaces in the Z direction, which back to the original object is like the out of this page in the up direction. So where this is positive down here, we've got one coming out pushing up, and in this corner coming out pushing down to counteract this stuff. Yeah. And what about stress in the Y direction? This is where we've got some big numbers, right? This is what's responsible for producing that moment. Remember that we said to get this to hold still, if we don't put these forces there, then we're going to need to have, let's see, how do we cancel those things? I think the last things I drew, oh, good. Okay, so if we cancel those forces, then the bottom fixed support will have to put a 50 Newton force here and a moment on the bottom, which is enough to cancel the 100 Newton meters, right? So this is itself 100 Newton meters. but in the opposite direction to the moment created by those two forces. So with this showing up now, how that's represented inside FlexPDE is with this axial force. So we have a big stress on, let's see, how to get this all in the page at once. We'll copy this and we'll say part E maybe. I think part E was to explain this. So part E, maybe I'll check that actually. We're jumping around a little bit. Part E, with reference to this, what does the reaction at there do differently to achieve static equilibrium in each case and why? Yeah, totally. Okay, great. So with reference to the contour plots, when we apply the forces on the sides to put it into pure shear, which is this setup, then the the surface at Y only needs to apply a shear stress to produce a shear force to the left of 50 newtons. And that's why only SXY was non-zero. But in this situation, bottom needs to apply a moment as well. And that means this is why the axial stress is non-zero and has a large range. So looking at this, we would need to have it to be compressive on the right side, pushing out, high compressive on the right side, and high tensile on the left side. Let's have a look. Yes, so very tensile on the left, very compressive on the right, pushing out there, and pulling in on the left to stop this thing from rotating. So that's what's going on there. The other thing is, because it's rotating, it kind of wants to buckle a little bit, like to bend out in the middle here and pull back in on the tops. And that's what's going on. That's kind of what would be modifying the stress in the X direction. So you see this going on here. We've got in the middle, we need to apply more stress. Let's see. So I'm claiming that the wall would want to make this thing move more to the left. So we have to produce stress to cancel that, which means on the X, well, this is the negative X surface. On the negative X surface in the negative Y direction, we will need to have, so do we need to have more stress this way to stop it from, I think we'd actually want to have more stress in the other direction, which is not what we're seeing. So I guess my intuition was not correct about that. This is the set of extra stress stuff on Y equals 0, which means that we're pulling it more to the left from the wall. The wall is trying to pull it this way, stopping it from buckling in the other direction. And the bottoms here, bottom and top, are being pushed more to the right. So with the negative stress there, the wall is pushing it to the right at the top and bottom and pulling it to the left in the middle. And if the wall has to do that, that means if it were to let go, this thing would want to bend out and push to the right there. Interesting. So that's kind of the opposite of what I would have expected from this curling around like this. Well, let's see if we can explore a little bit by changing around the boundary conditions and seeing if we can allow some of that stuff to happen. Another thing that's going on in this code here is that the compression that's happening on the right side is being prevented from expanding up and down and to the right, and so there's some interesting stuff going on here in the Z direction, and the tension on the other side is trying to compress in, so making it like shrink there. So we've got something that wants to expand on the right and compress on the left. So maybe that does explain why it would actually want to be buckling in the other direction, and that's what we're preventing here. Let's see if we can explore this a little bit. So we might be able to say instead that it holds still not on this side by setting the Z displacement equal to 0 everywhere on that side, but instead saying the Z displacement is just leaving that alone, right? What if we get rid of this Z boundary condition? Now it's not constrained in Z, it might be moving around. Aha. So there's the expansion and the compression. It sort of forms this parallelogram a little bit, or a trapezoid, right? So when we don't stop it from expanding and compressing in Z, then it does that a little bit. And you can sort of see the buckling. This gives you the impression that it does want to buckle the opposite way to what I was thinking at first. And shows that now there isn't any stress in Z because we're not restricting it, and it would be forming into this trapezoid from its from what it needs to do to produce this moment. Can we try and get rid of this as well? Yeah, let's see. So if we'll still say value v is equal to 0 to hold it still there. What if instead of value u is equal to 0, we just put load u is negative s applied? We just apply the shear stress that's going to cancel it, and we don't actually resist any motion to the left and right on this surface. This is going to make the displacements incorrect because there's no reference point for u equals 0, but it might. No, it looks like it didn't work that time. Okay, yeah, so that totally crashed FlexPDE, but sometimes it'll work. Let's try again. Aha! So reopening the program, now it works, and you can see the buckling that was prevented. So the displacement is not meaningful anymore. We're just lucky that it didn't zoom off to infinity. There's nothing holding it still in X anymore, so it might not work at all. But this, if you can get it to work, sometimes it takes a couple of tries, then it'll show you the buckling that's actually happening. So this is not what I expected. I expected when you pulled on it there and got it to bend, it would attempt to buckle in the opposite direction. But here the displacement is so low that we're just applying this compressive force on the right, and that gets it to expand over there, and tensile force on the left, and that requires compression, meaning that the wall anchor, other things equal, would tend, at least at first, to buckle kind of the other way. And that's what it's all about. This is challenging those expectations. We see something that at least I didn't expect here, and then explore the heck out of it and see how it leads to some interesting results. Oh, this I accidentally scrolled into the old solutions, and you might know that this one has the opposite color from what we saw in the solutions we just did. So if we just go back to the old value u is equal to 0 on that surface, this will still have the trapezoid, but it didn't change what was going on in the X direction of stress. Sometimes it crashes and you gotta load it up again. Yeah. So here we go. Right. So this is the opposite color of what's going on there. We had the opposite stress, but wait a minute. Nope. It's just the color scale is different. So this code in the practice problem solution is using an option in select called spectral colors, I think. Oh, how did you do? Well, it's definitely not with a U. What was the code for that? Spectral colors? It's with an underscore. Spectral underscore colors will now make the colors look kind of like this. So you can make it so red is the lowest and purple is the highest, instead of the default, which is red is the highest and purple is the lowest. There's also maybe thermal colors. Let's see what this looks like. Okay, so that's just the default one, where we go to red being kind of hot and blue being cold. Right. So when you look at the plots there, some of the code might be using thermal colors and some might be using spectral colors. So spectral colors, why is it called spectral colors? That's to do with the light spectrum. So in optics, purple is like the highest energy, right? Red is the lowest energy. But you tend to think of a heat map kind of the opposite. Like if you see blue on a weather map, and then you see other places where it's red, you're like, oh, the red is hotter. But in terms of light energy, blue is higher energy than red. So from a spectrum perspective, this is the where the highest numbers are, and red is the lowest. Yeah. So the color doesn't mean much if you don't also look at the color bar. All right. So that's it. Thanks for watching, and I'll see you next time.